the timing for the session is 11 a.m. to 1 p.m. So it's already 11, but I'm waiting for a couple of minutes so that people can join. If not, I will start the session, and I'm also recording the session in case it is required. I'll wait for 5 to 10 minutes. If not, I will start. So it is already 11:05, so I'm starting the session. If people want to join, they can join in the middle. I'm also recording the session in case it is required. So as per the suggestions of NPTEL team, I might upload this session. So hello everyone, welcome to the course Sensor Technologies, Physics, Fabrication and Circuits. So this is an extra session for this course. I am also taking the regular problem solving session, the weekly sessions on Tuesdays. But this is an extra session. Some of you have asked if we can have a summary session at the end before exam. So this is for that. Okay, someone has joined. Yeah, hi Pratik, I'm just starting. So I was waiting because there was no one in this meeting. So this is an extra session, like apart from the regular ones, regular weekly sessions. So I'm just taking this extra session for, it's like a summary session. I will cover the summaries from week 1 to week 7. For week 8 we will have another class on Tuesday, so I'm not covering that. So I will try to give basic overview of the topics those were covered in this week, from week 1 to week 7, and will solve a few problems related to the topics those were covered in each of these week. So let me introduce myself first. I am Ananya, a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. So my specialization is microelectronics and VLSI. I'm not working on sensors specifically right now, but I did work little bit on sensors during my MTech thesis. And also right now I'm working mainly on fabrication, like fabrication of different devices. So let's start. If you have any question in between, you can write in the chat box. I will try to answer that. And you can unmute yourself and speak also. I will be in the presentation mode most of the time, so may not be able to check all the messages in the chat box. So I hope that I am audible and you can see my screen clearly. So let's start. Okay, so the topics those were covered in week 1 are this. So first the week started with some basic definitions related to sensor and like different terminologies associated with sensor. So first, what is the definition of a sensor? So there is no unified definition, but briefly we can say that a sensor is a device that detects changes in its environment and converts the changes into an electrical signal or other readable data. So if we consider sensor like a black box, so this is a sensor. So the input and output for this is so input is environmental change. It can be anything like change in temperature, changing say the gas concentration environment, something like that. And the output is electrical or other readable signal. Or signal in any readable format. So what an other readable format can be? It can be an optical signal, it can be like a mechanical signal like deflection of something, like a pendulum. It will move back and forth, so that the frequency by which it moves, like it oscillates, that also give us some indication maybe not maybe exactly very quantitative information, but it will give qualitative information. Say if the frequency increases, the speed of oscillation increases, it indicates something. So just by looking at that, we can get some indication about the environmental change, whatever the input parameter it is trying to detect. Next definition was transducer. So what is a transducer? It is a device that is able to convert one form of energy to other. So how it is related to sensor? So in case of sensors, most of the sensors are electrical in nature. Why we prefer electrical or electronic sensors? Because the output of these sensors are electrical signal. We get either change in voltage or change in current or change in conductivity. So these are very easy to, like as I mentioned earlier also, that it is very easy to make a system out of an like electronic sensor, because we can easily convert the analog voltage signal or current signal to equivalent like digital values, and based on that we can take some decision. Say your output of your sensor is an electrical signal which is a voltage signal. Say it gives a voltage 0 to 5 volt. So this is for minimum input signal, and this is for maximum input signal, whatever your input range is. Okay. And sorry, I cannot hear you properly. So if you have unmuted yourself by mistake, then please mute yourself, because it will create some disturbance. So I have just muted everyone, but you can write in the chat box and I will unmute after some time. So, okay. So this is your range. For some minimum input value you will get output as 0 volt, and for some maximum value of input you will get 5 volt output. Then you can convert it into a digital signal using an analog to digital converter, and say that will give you some value between 0 to 1023. So if it is like a 10 bit ADC, then say from 0 to a range to 55, you will say your input is low. Based on that you can do some decision, you can take some decision, say to turn on and off a certain motor or something. Then say from 256 to some 512 value, it is like in the middle. So it maybe it means do nothing or something, you can say. And then say above 512, it's very high, so it will raise an alarm or something like that. Based on that you can do a you can make a system automatic, you can like make a smart system, automatic system to do your work. Okay, so that is why we prefer electrical sensors or electronic sensors. So what it suppose you have one sensor, the output is not an electrical signal. Using a transducer you can convert that signal to an electrical signal and make a system out of it. Now next topic was classification of sensors. Now the sensors can be classified into different categories depending on various conditions. So say these are not limited, there may be other classifications of sensors also. I am just giving you a few examples. Say first one is analog to digital, analog and digital sensor. So these are based on say work like a type of the output signal. Okay, you know what is an analog signal, what is a digital signal. So if the output is analogous, then it's an analog signal. If it's in bit form 0110, then it is a digital signal. Then it can be a contact sensor or a non-contact sensor. So say you want to measure something, like measure the temperature of an object. So typically we connect the sensor to the object, so there is a heat transfer between the object and the sensor. So in that case, that will be a contact sensor. There can be non-contact sensor also. For example, if you want to detect the presence of some human being, so you can use a IR sensor in that case, because we radiate infrared radiation, like the electromagnetic wave radiated by a human being, that lies in the infrared frequencies. So that can be an example of non-contact sensor. So just from the radiation, or one example that was discussed in this series, in this course, was also acoustic sensor. That can be a non-contact sensor also, because there is no physical contact between the object and the sensor. Now, based on working mechanism of the sensor also, it can be classified into different categories. These are not limited to only resistive and capacitive sensors. There are other types of sensors also. So another type of classification is based on working mechanism. So in a resistive sensor, due to the environmental change, the resistance of the sensor changes, and in a capacitive sensor, due to the environmental change, the capacitance in the configuration changes. Now there can be different types of configuration in case of resistive sensors and capacitive sensors also. Those were discussed in the later weeks. Okay. Next was one thing we learned, that the multidisciplinary aspects of sensor, because if you want to design a sensor, it is typically it is an electronic sensor, so you definitely need you should have some background of an electronic system. So for example, the last week is on circuit part, or the interfacing circuit for a sensor, that requires, say, a filter component and amplifier. So you should have some electronic knowledge, but then if you are designing a sensor for biological or biomedical application, then you should have that knowledge also. Say a particular antigen and antibody, so you are trying to detect a particular antigen that you will detect with a particular antibody, so you should have that knowledge also. And also, say if you are designing a chemical sensor, you should have some knowledge about chemistry. And also this course is on physics, fabrication and circuit, so there is a fabrication part also. So you should have those knowledges about those processes also, different fabrication processes, because ultimately you not only want to design a sensor, you want to make it and use it for some practical applications. Then different terminologies associated with sensor that was started. So first was accuracy. So what is accuracy? How accurate or correct the measurement is. So this figure explains what is accuracy and what is precision. So what precision is, how narrow the distribution of measurements are. So suppose for some, say your input is fixed, so you are measuring the temperature, like the boiling point of water. So your outputs, so you will get some output. Say if it is a electronic sensor, you will get some voltage level that will correspond to some input. So that should be 100 degrees Celsius if you are measuring the boiling point of water. So say this is your input axis, so this should be 100 degrees Celsius. And since you are measuring the boiling point of water, every time you measure, it should give 100 degrees Celsius. So this is your actual value, actual target or reference value, and but you are getting different. So say you did measurement 1, that will give some 105 degrees Celsius. So that difference is inaccuracy, or you can calculate the inverse of it, which is accuracy. Now what is precision? Suppose you are doing the measurement multiple times, say for some like for measurement 1, this is your 105 degrees Celsius, that was your value. Say some for measurement 2 you are getting 101 degrees Celsius, and for say measurement third measurement you are getting 107 degrees Celsius. So this distribution is known as like this distribution is involves of precision. So if it is very narrow, then we say that the sensor is precise, and if it is broad, then the sensor is not very precise. Now if your characteristics say is like can be like this also, say this is your target value and you are getting a distribution like this. So this sensor is accurate, but it is not very precise. Next, in this case, if say it is your reference value and you are getting another value at some point, but your distribution is very narrow, say, so this sensor is not very accurate, but it's very precise. So these two terms are not same. So after that, what we studied, the calibration of a sensor. So why we need calibration of a sensor? So what calibration give us? It is the relation between output and input. So if your output is capital S and if your input is small s, so the function, the relation by which the input and output is related, that is given by calibration of a sensor. Now why you need the calibration of a sensor? Say if you have a resistive sensor, so the resistance is rho L by A. Now say due to stress and strain, this L is changing. It may be compressed or it may be like expand due to some force. Now how much it will expand and how much it will contract, that will depend on the material property. What is the like Young's modulus, Poisson ratio, all those terms will come. But you don't want to you don't know those material parameters. Say you don't know what material is inside your sensor. So what you will do, instead of going to the physics part of the sensor, you will instead of understanding like how the sensor will behave from physics point of view, you will do an experiment. You will like have a data, like you will give some input, that will be your known input, and you will get some output. This will be your force, say it will be in Newton, and output you will get as change in resistance or as resistance. So you can get a curve. This will be say force and this is delta R, so it will be something like that based on the material and type of the sensor. So even if you don't know the material parameter, even if you know the physics how the sensor is working, you will be able to say that if delta R is this, my input is this. So calibration helps us to get like to use a sensor even without knowing what is happening inside of a sensor, like how the sensor is actually behaving. So these were the topics those were covered in this week, in week 1. Is there any question? I think I can unmute now, people. Let me see if I have missed something. Okay. So apart from that, in week 1 we have also seen different components of a sensor. So what are different components? We typically have a substrate on which we will have our sensor. So the substrate can be rigid or flexible. Now depending on where you will be using your sensor, say if you want a wearable, if you want to make a wearable sensor, if you want to you use it as a like a watch, say similar to something like a watch, then you will need a flexible substrate. And we have also discussed what are different flexible substrates, say PET or polyamide. Now all these substrates can handle different temperature. suppose if you want to use for some industrial application where the temperature range, working temperature range is very high, then you will need a sensor, you will need a substrate that can sustain very high temperature. Now in most cases the flexible substrates cannot handle high temperature. Polyamide is one substrate, so that can handle a little bit high temperature, again not very high. So maybe you can use it up to 300 degrees Celsius, or like in that range. Definitely not very high, say 500 or 600 degrees Celsius. You cannot use a flexible substrate, at least not that I know. Maybe there are some specific material that people use for space application and for specific applications, but those are not very easily available, and maybe not very cost effective because those will be expensive. But you have other options in case of rigid substrates. Say you can use a quartz substrate that can handle very high temperature. So based on your application, you will decide your substrate. Then another component in a sensor will be your sensing material. That can be like a sensing film, metal oxide, semiconductor based sensing materials. Those are very common in many cases. So you use different materials which are sensitive to environmental change, say ZNO, SNO2, all those things. And apart from that, we typically need electrodes on our system, on our sensor, because you want to measure resistance. Say if you want to measure capacitance, so you need two electrodes. Now how to make those, like how to deposit those sensing material on a substrate and then to make the electrodes, here comes the fabrication part. So you do deposition and you do patterning for the electrodes, so that you get the final device. So I think I have covered most of the topics. Those were discussed in week 1. So let's take one question. I will write the question first. Which of the following sensors is used for non-contact temperature measurement? First option is thermistor. Second is thermocouple. C is infrared sensor. D is RTD. So what is the correct answer? Can you tell me the answer in the chat box? A, B, C or D? Infrared sensor, yes. So what is the working mechanism in case of an infrared sensor? So here answer is C, infrared sensor. So in all of these other temperature sensor, thermistor, thermocouple or RTD, there will be a physical contact between the object for which you want to measure the temperature and the sensor. But in case of infrared sensor, it is based on the infrared part of the electromagnetic radiation. As I mentioned that like any object which has a non-zero temperature will radiate infrared radiation, like infrared frequency. Now you have infrared sensor, you can have an infrared camera that will detect the image, and based on that you can say the temperature of this object is something. So the power generally achieved by a sensor, by an infrared sensor, or infrared camera is also kind of like a sensor. That depends on temperature. It is not linearly dependent, so it depends, I think it is related, it is proportional to T to the power 4. You can see the formula, so there is a formula, I don't remember exactly, but based on the power you can say the temperature is like that. So just give me a minute, I will confirm it. Yeah, so the power radiated by a non-zero by an object which has a non-zero temperature, so that is proportional to T to the power 4. There are other parameters also, it is a proportional. So T is the temperature of the object, so it is related to the power by this relation, and so based on the power achieved you can say that the temperature of the object is so and so. Okay, so this law is called Stephen Boltzmann law. If you are interested you can look into that. So for non-contact measurement, this is one way to do the measurement. It is useful in many cases. Say uh, if your that temperature is very high, so you maybe you don't want, or if the object is in a say hazardous situation, you don't want to directly put your sensor there, you want to monitor it from outside. In that case this kind of non-contact measurement can be useful. Okay, so let's move to the next week, week 2. So week 2 mainly covered different sensor characteristics. So first one is that was discussed was threshold. So what is threshold? It is the minimum detectable input. So threshold and resolution is different, that I will discuss. Threshold is the minimum detectable input. Suppose you have a temperature sensor, the range is from 0 to 300 degrees Celsius. So if it is a negative temperature, say minus 10 or minus 20 degrees Celsius, that your sensor cannot measure. So in that case your threshold of your sensor will be 0 degrees Celsius. Next topic was offset. So what is offset? It is the output when input signal is 0. So you are not applying an input signal, whatever the offset you are getting, whatever the output you are getting, that is known as offset. So what should be the unit for an offset? Suppose the question is given that calculate offset for the sensor, then like will calculate it, will put the input signal as 0, you can calculate what is the output value, and the unit for offset will be same as the unit for output signal. Okay, next was range, the minimum and maximum input of a sensor. So it does not mean that your sensor will not work outside your range. What it means is that the calibration curve, the relation between input and output you are getting, so capital S is equal to some function of small s, so this is input, this is your output. So your this calibration relation, the equation by which you are correlating input and output may not work, okay, in outside this range of the sensor. So typically you do the calibration for a certain range of input, and within that range you define a like your input output relation using an equation. Okay, outside your range also the sensor will give some output, but it will not follow this input output relation. Next is linearity and non-linearity. So as the name suggests, if your input output relation is linear, then the sensor is a linear sensor, and if the input output relation is non-linear, then it's not a linear sensor, it is a non-linear sensor. And in many cases So typically we want a linear sensor because it is easy to implement a linear sensor. You will not need many components to implement a linear sensor. So that is why we prefer a linear sensor, and we try to fit our input output relationship using a linear, like straight line equation. And if my output is deviates from that straight line, that measurement, so that quantitative term is known as non-linearity of the sensor. Okay. Next was hysteresis. So what is hysteresis? The change in the response due to the measurement in different direction. So what it means, that if you are measuring, so this is your input signal and this is your output, and you are increasing the input, say from 0 to some maximum value, the sensor is giving some output like this, in this fashion. And say you are decreasing the sensor input from maximum value to minimum value, then it is giving a curve like this. So during when the input is decreasing, so this loop is known as hysteresis loop. So ideally in many cases we don't want hysteresis loop, especially in case of sensor. We don't want any change in behavior due to the direction of measurement, but in many cases this can be useful. Okay, so you know that in case of magnetic material we get hysteresis. You have seen the hysteresis loop in case of magnetic material. So in wherever you get hysteresis loop, there is something like memory effect. So these are mainly used in case of like memory devices. So if you are interested, you can look into it. So anything that gives hysteresis can be used as a memory devices. But in case of sensor, we don't want hysteresis in most cases. Next term is selectivity. So if you are designing a sensor to measure certain environmental change, then it should measure that change only, not other change. Okay. So if you are designing a resistive sensor where the resistance of the sensor will change based on the temperature, now the resistance of a sensor can be the resistance can be changed due to some other environmental parameters, say due to humidity and other environmental condition, the sensing material is degrading. So that can also give a change in resistance, but you don't want that. Say due to humidity, you don't want to get a change in your resistance value, you want only due to temperature. In that case, your sensor will not be very selective. So this term is also very important in case of chemical sensor. Say if you want to measure a certain type of gas, say if you want to measure say carbon dioxide gas, you want the response of a sensor to be changed due to only carbon dioxide gas, not due to carbon monoxide or other gases. So selectivity is very important in that case, and if you have to ensure that your sensor is selective to the only parameter that you are in for which you are designing the sensor. Okay. Next two terms are repeatability and reproducibility. So these terms are similar, but what repeatability means, that if you are doing the measurement using your sensor repeatedly, like you are doing continuous measurement, you are turning on and off, say you have a gas sensor and you are introducing gas at this point, you are removing your gas at this point, again introducing at this point. So this is time axis, and you are removing your gas at this point. So your sensor should give input at this instant. Ideally it will not be like a square wave, it will be something like this, but I'm just considering an ideal response. So it will give some output. Once you remove your input signal, then it will become again 0, it will again give output, and this should repeat. Now this output level, since your input is same, you are giving same input at this point and this point, so your output level should be same. It should not decay, like it should not become something like this. So this is the repeatability. Now reproducibility is that you are doing the measurement, but maybe not in the same day. You are measuring today and you will measure tomorrow. The result should be same if you are giving the same input. Again, you are measuring it today and someone else is measuring it also today, the operator are different, then also it should give the same result if the input is same. Again, you are measuring this in a very, say, hot climate, and someone is measuring it in a different climatic condition, say in Kashmir, where the temperature difference between your place and there is, say, 10 degree. So there also, if the input is same, then the sensor output should be same. That is known as reproducibility of the sensor. Okay, so this is the difference between these two terms. Many times these are used interchangeably, but these are not exactly same. Next, deadband. So it is the range where the sensor is insensitive. That means the sensitivity is 0. So sensitivity is delta output due to delta input. This is 0 in case of deadband. Okay. Next, resolution. This is the smallest change that can be detected by a sensor. Okay. Ideally, we want very high resolution. That means the value of resolution should be very small. Now again, it depends on your application. If you want to detect, say, 1 degree of temperature change, then you want a very good sensor that will give very good resolution. But say if your process is not very critical, you want to detect your temperature between, say, 100 to 150 degree Celsius, then even if your resolution is not very good, that in that case also it will work. Now everything depends on your application, and based on that the cost of your sensor will be different. So if you want a very accurate, very precise sensor that can give low resolution, that may be more expensive. But if your application does not require that, why you will go for a costly sensor? You can use a different material, you can use a different sensor that can give reasonable accuracy and precision and acceptable resolution. Okay. Next, we studied dynamic and time dependent response of a sensor. So as I mentioned here, you introduce your input at this point, the sensor output will not go immediately to the final output value. So that is like the dynamic or time dependent response. And then in that part also we studied response and recovery time. So what is response and recovery time? Say if your input is like this, which is like a square wave, this is your input, this is the time axis. Okay, but your output is something like this. Okay, so this is the 100% of your input, this is the ideal output, say, and this is 90% of your output. So this time it takes to reach 90% of your final signal, that is known as response time. And recovery time is that once you remove your input, the output will decrease and it will reach the 10% of your final final signal when there is no when there is no input. So from this 100% output signal to 10%, that time it takes, that is known as the recovery time. Okay, so these are very important. So in ideally we want a very small response and recovery time, and in many cases these timings can be in microsecond or nanosecond. If the response and recovery time for a sensor is in seconds or minute, it's not a very good sensor. Now again, it depends on your application. If your application does not need very fast response, then you can have a sensor where the response and recovery time is in seconds also. Okay. So these were the topics for week 2. is there any question? I will take a pause if there is any question. So let me give you a question. So say there are four temperature sensors. The input output relation is like this. So the R in ohm, this is your output signal, and input is temperature. Okay, so say it is in Kelvin or degree Celsius, can be anything. Now for sensor 1, the input output relation is R is equal to 4.7 T. For sensor 2, R is equal to 1.25 T plus 7. Sensor 3 is R equal to 2.4 plus T plus 10. And sensor 4, R is equal to 5T plus 6. So which one is more sensitive? And which one have lowest offset? Okay, so this is the question. Again, give me the answer in the chat box. How we will calculate the sensitivity of the sensor? We will how we do, so these are linear sensors. In that case, whatever the slope of the line, that will give us sensitivity. The general formula is the sensitivities change in output due to change in input. Now the offset, how we calculate, so the offset is when the input is 0, so we put input as 0. Whatever the output we get for 0 input, that is the offset of the sensor. Ideally, we want high sensitivity and low offset. So which one of these sensors are better in terms of sensitivity and in terms of offset? What is this jam file of the meeting? More sensitive is sensor 4 and lowest offset. At least I am getting some answers. So to find offset, we will put t is equal to 0. So this is for sensor 1, offset is 0. For sensor 2, offset is, so this is ohm, right? The output is ohm. This is 7 ohm even when your temperature is 0. For sensor 3, this is 10 ohm, and for sensor 4 it is 6 ohm. So lowest offset is this one. Now sensitivity, this is the slope of the sensor. Slope of the sensor, because these are linear sensors, okay, everything is linear. So the sensor has characteristics like y equal to mx plus c. So m is your slope, okay. So for sensor 1, sensitivity is 4.7. The unit is ohm per Kelvin per, so temperature unit is given as Kelvin, okay. For sensor 2, it is 1.25 ohm per Kelvin, and for sensor 3 it is 2.4 ohm per Kelvin. You should write the unit also. So for this one it is 5 ohm per Kelvin. So this has highest sensitivity. Okay. Now there you can see there is a trade-off, like this has highest sensitivity but this one has lowest offset, so you should decide based on your requirement. Okay. So next week in week 3 we discussed capacitive sensors and thermal sensors. So first is capacitive sensors. Now here due to the change in environment, the capacitance of the sensor can be changed. Now there can be different capacitive configuration. The basic one is parallel plate capacitor. In that case capacitance is given by this formula, epsilon naught epsilon r A by D. So where epsilon naught is permittivity of free space, which is 8.85 into 10 to the power minus 12. This is farad per meter. And epsilon r is like relative permittivity of the medium that is in between the parallel plates. A is the cross section area and D is the distance between the plates. Now the capacitance is a function of, so epsilon naught is a constant. Now it is a function of epsilon r, area and D. So any of these three we can change. So if there is a change in any of these three, there will be a change in capacitance, and we can correlate the change in capacitance to equivalent change in epsilon r, A and D, and based on that we can design a sensor. Now here we have also discussed about interdigitate kind of arrangement where the capacitance is, so the configuration is like this. So you have this ohms like electrode, okay. So this is one electrode and this is another electrode, and there is a capacitance between these two electrodes, and overall the overall capacitance is given by this formula. So if there are n number of electrodes, so in this case there are 6, so the formula is n minus 1. In this case it will be 5 because there will be a capacitance between these two, 2, 3, 4, 5. So total capacitance is n minus 1 epsilon naught epsilon r A by D. So this kind of electrode is often used. So this is known as interdigitated electrode, and this electrode configuration is often used. So this is the formula. I think you have solved some questions using this formula in one of your assignment also. This is one of the possible geometry. There are other possible geometries also, cylindrical type of capacitors that also was discussed. I've also discussed in the live interaction session for week 3 also. We discussed one problem related to that. Okay. Next topic was thermal sensors. Now, what are the thermal sensors? We know RTD, thermistors, thermocouple, infrared sensor also we have seen. So, thermal sensor basically detects temperature, change in temperature. Now, most of the thermal sensors are resistive type sensor. So, those are known as thermoresistive sensor. Okay, so most of these are thermoresistive sensor, and there are different types of sensor, but the basic the physics part of is that suppose you have one object. So this is your object, it has some temperature TB, and you have your sensor. So this is your sensor, and the temperature of the sensor is Ts. Now ideally you want the temperature of your sensor is equal to the temperature of your object, but there is something called thermal resistance, because of which the heat will not be transferred to your sensor like very efficiently without any loss. So that this term is related to that, that is the physical significance of thermal resistor. And there is also a capacitor, like the temperature will don't want to, like there is a capacitive effect, so there is kind of a delay. So that is why this RC kind of configuration we get. And then there is this environment. So there may be heat transfer from environment to object, and there will be like heat dissipation from sensor to environment also, that is denoted by this R2, which is the thermal resistance between the environment and the sensor. Now ideally we want the sensor temperature to be exactly equal to object temperature, which is very difficult to obtain. So general equation in static conditions, so this is in static condition, the temperature is not varying in any of these three, like T0, Ts and Tb is not varying. In static condition, the equation that is given, Ts equal to Tb minus delta T into R1 by R1 plus R2. Okay, so how we can arrive at this equation, that was discussed. You can refer to the lecture note, but this is the equation. Ideally Ts should be equal to Tb, but it is not that case. So delta T is Tb minus T0, the temperature difference between the environment and object. So there should be a heat dissipation from object to environment, or environment to object, or like there will be heat transfer. Okay, so this delta T term is not exactly equal to 0 all the time, actually most of the time. And then this is related, this is another term. So R1 by R1 plus R2. So if R2 is very large, so this equation becomes Tb minus delta T R1 by R2. So typically we design our sensor in such a way that the thermal coupling between the object and the sensor is very good. That means R1 is very low. Heat can easily transfer between the object and the sensor. Okay, so that is why we are considering R1 as low. If R1 is very high, then the heat will not reach from your object to your sensor, then the sensor will not be able to measure the object temperature accurately. Again, we want a very large R2, because we don't want the heat dissipation between Ts and T0, like the sensor and environment. We want only to heat transfer between object and sensor. So there should be a decoupling between the sensor and the environment. Okay, so this is the equation. Now we get sensor temperature, we can get sensor temperature is equal to the object temperature only when delta T is 0 and R2 is very very high, or R1 is 0, like ideally, which we cannot achieve practically. So this is in static condition. Now in case of dynamic condition, dynamic condition means the temperature of the sensor is changing. Like we have some object temperature, but the temperature of the sensor is reaching towards the object temperature. So this is Ts and this is the time axis. So this is the dynamic case. In that case, so what is the expression? So the sensor temperature is given by Tb minus, so this is exponential kind of a relation, delta T exponential minus T by tau. So this is tau is the time constant. Again, how we can reach to this expression, that was discussed in the lecture series, but the point here to remember for you is that the derivation you can look, but the final conclusion is that in case of dynamic condition, the temperature of a sensor like takes this form, like exponential raise kind of form, and tau is an important term because it is the time constant based on which we can, like if you want to measure the sensor, like if the sensor temperature should be stable enough so that we can say that it corresponds to this object temperature. So typically we consider, we do the measurement, we do the reading after 5 tau to 10 tau, because after 5 tau to 10 tau, if you put here in the expression T is equal to 5t or 10t, you can see that you will see that this term is very very negligible. So we can say that our sensor temperature is almost equal to object temperature. Okay, now you can do this exercise by keeping T is equal to 5t, and you can do the same exercise using T is equal to say tau and 5 tau. You will see the difference. So there will be in T is equal to tau case, this will not be very close to Tb. In T is equal to 5t, it will be reasonably close. Okay. Yeah. So these were the topics those were covered in week 3. I hope there is no question. So I am trying to give like 1 or 2 questions for each week. So this is one question related to the topics of week 3. So which of the following statement is true? Is or are true? So the dynamic condition of thermal sensor follows an exponential relation. This just I discussed. Higher time constant relates to a faster response. A third statement is to have a faster response, specific heat of the sensing material in the thermal sensor must be high. And the last statement is at steady state for finite thermal resistance between sensor and object, sensor can reach to object temperature provided thermal conductance between sensor and environment is 0. So these are the options. So which of these statements are correct? So which one is the correct option? You can again tell me in the chat box. Option C. So that is the correct answer, but look at all of those statements. Let me take one by one. So what is the first statement? Dynamic condition of thermal sensor follows an exponential relation. So what is the dynamic condition of a thermal sensor? So Ts is equal to Tb minus delta T exponential minus T by tau. So Tb is the object temperature, Ts is the sensor temperature, delta T is equal to Tb minus T naught, the thermal gradient between the object and environment, and tau is the time constant. So what is thermal time constant? Tau, and it is given by mc by alpha 1. So what is m? This is the mass of the object. C is specific heat of the material of your sensor, and alpha 1 is thermal conductance. Between object and sensor. Now this expression is pretty intuitive, you can say that. So mass of the object, if so tau should be small so that it reaches the sensor temperature, reaches the object temperature quickly, right? If the mass of the object is more, that it will take more time for heat dissipation, so that so it will take more time for the heat to reach the sensor. Okay, so it is directly proportional, it will increase the time constant. Now if the specific heat of the sensor material is also high, that will also increase the time constant. What is specific heat? It is the amount of work you have to do to increase the temperature of any material by 1 degree Celsius. So if your sensor material is it the specific heat is large, so that means you have to put lot of effort to increase your temperature, increase the temperature of your sensing material, then also your time constant will be more. Then alpha 1 is thermal conductance between the object and sensor. If heat can easily transfer between your object and sensor, then again it will take less time to heat the sensor. Say if your object temperature is high, then it will take less time to heat the sensor also. So it is inversely proportional. So this expression, just by looking at it, you can say that like if I give you the terms m, c and alpha 1, you will be able to get the relation. So which one is directly proportional and which one is inversely proportional, right? Thermal time constant. So this is the expression in case of dynamic condition. So this is true. Dynamic condition of thermal sensor follows an exponential relation. Next is higher time constant relates to a faster response, which is not true. I mean, it will increase the delay, right? It's like very straightforward in that way. Third statement is, so statement 3, let me write. To have faster response, specific heat of sensing material in the thermal sensor must be high. So again, specific heat is C. So higher the C, higher will be your tau. slower will be your response. Okay. So why specific? What is specific heat? It is the heat required. I mean, heat is the energy to raise the temperature of, I am just writing the definition, 1 gram of material by 1 degree Celsius. Okay. If your sensing material needs very high energy to raise its temperature, then definitely your sensor response will be slow. So these are the things you should consider in like you should keep in your mind if you are designing a thermal sensor. You want a material that has low specific heat. Okay. So this is not true, right? And at steady state, for finite thermal resistance between the sensor and object, the sensor can reach to object temperature provided thermal conductance between sensor and environment is 0. So let's see that. So this is in steady state, that is in static condition. So in that case, your sensor, this expression is TB. So I will write approximately equal minus delta T R1 by R2. So what is R1? So this is your object. This is R1, this is your sensor. There is this capacitance. This is your environment. So this is R2, this is R1, right? Now Ts will be equal to Tb only when delta T is equal to 0. So that means Tb is equal to T0, and if R1 is finite, that is in the question, right? Finite thermal resistance between sensor and object, that means R1 is finite. Ts will be Tb only when the thermal conductance between the sensor and environment is 0, that means R1 is infinite. R2 should be infinite. Then only Ts and Tb will be equal. So R2 should be infinite means the thermal conductance between Ts and T0, that is sensor and environment, should be 0. So this statement is also true. So our correct answer is C. I hope there is no question in the topics those were covered in week 3. So let's go to week 4. Again in week 4 we discussed thermal sensors. Most thermal sensors are of resistive type, so these are known as thermoresistive sensor. Now thermal sensors can have either positive or negative temperature coefficient. So it can have PTC, which is positive temperature coefficient, NTC, negative temperature coefficient. Now we discussed about different types of thermal sensors in this week. So One is thermistor. Thermistors can have both PTC and NTC. Okay. Thermistors can be made up of different material, like semiconducting material, ceramic material. So based on your material properties, it can have PTC or NTC. Most of the thermistors are NTC type, that shows negative temperature coefficient. There can be some PTC type thermistors for some material, and those are mainly used as a like a resettable fuse in case of electronic circuits. So what happens, as the temperature increases, the resistance becomes very high. So if you place a thermistor in your electronic circuit, the resistance will be so high that it will not allow for current to pass. So current will be very negligible or almost equal to zero. That is how a fuse works. So what a fuse does, if there is some abnormality, say very high, some temperature from some voltage fluctuations or something, then it just breaks, so that the current is zero, the circuit is incomplete and the current is zero. It saves your other electronic part, right? So that is that's why we use fuse in our electronic system. So instead of a fuse, if a thermistor is used, when the temperature is very high, the resistance will be very high. It will almost act like a fuse. The current will be negligible. It will save our circuit, which is after the thermistor. And the advantage is that it will not break like the most fuses. How it works, the wire kind of melt. So if you have seen fuse, like when it becomes bad, like the wire actually melts. But in case of thermistor, the resistance will be very high, so you can reuse the same thermistor again. At low temperature, the resistance will again come back to the normal value. Okay, so that is one use of PTC type thermistors. Next, we discussed about RTDs. Okay. RTGs are mostly PTC type, positive temperature coefficient type. So the material that is used in RTDs are mostly metal. Okay, in most cases it is platinum. Can be other material also, nickel or copper, but platinum is mostly used. And these are used for high temperature, because metals can sustain high temperature compared to the materials. Those are used in case of thermistors. So the working temperature range is very high in case of RTDs. Okay, but these are expensive, as you know that platinum is expensive compared to the materials those are used in case of thermistors. But the advantage is that these you can use for high temperature applications. So next, we discussed chemical sensor. In chemical sensors, the classification can be done based on physically reactive or chemically reactive. In case of physically reactive sensors, when the chemical reactions happen, it will change some physical property of the sensor. Say it increases the stress in the sensing material, strain in the sensing material. Or in case of chemically reactive sensor, due to the chemical reaction, some electrical property, say conductivity of the sensor, those things get changes. Now there can be direct and indirect sensor. So how these are classified as direct and indirect? So in case of direct sensor, the output of the sensor is an electrical signal. In case of indirect sensor, we'll use a circuit or a transducer to convert the output of the sensor to an electrical signal. Okay, so that is a difference. Now there can be different configuration. Also based on that, also we can classify chemical sensor. One type is MOS sensor, where you use some metal oxide semiconductor sensors, like material like ZNO or SNO2. The properties of these material changes due to some chemical reaction, and that can give indication about the reaction that is happening. So these are one type of chemical sensor. Then field effect transistor type sensor. So in a field effect transistor, you all know about MOSFET. So in case of a MOSFET, there will be a source, there will be drain, and there will be a gate terminal, right? So this is gate, this is say source, and this is drain. So the current between source and drain will depend on the voltage at the gate terminal. Now the potential or the voltage at gate terminal can be changed due to some chemical reaction. So our current like with the current between source and drain, IDS, that will change based on gate potential, and that we can correlate with the concentration of the reactant molecules, those are on top of your gate terminal. So this is also one configuration. There can be other types of chemical sensors also, there can be different types of classification, but these were three, those were discussed in the lecture series. Next topic was electrochemical sensor. So electrochemical sensors can be amperometric, potentiometric, or conductometric. So in case of amperometric sensor, the basic definition is the current in the sensor is a function of the analyte concentration. So as your chemical reactants, the concentration of your reactants will change, that will change the current. So this is current, like I, okay, that will change. In case of potentiometric sensor, the potential or voltage is a function of the analyte concentration, and in case of conductometric sensor, the conductivity is a function of analyte concentration. Okay, there can be different configuration, different types of electrode, and those were discussed. I will not go into details of that, but this is the basic definition of electrochemical sensor, where due to the chemical reaction, some electrical property, either current, voltage, or conductance gets changed due to the chemical reaction, due to a change in the different concentration of your reactant molecules. Okay. So let's see if I missed something. I think this was enough. We'll give one question. Which of the following factors can affect the performance of an electrochemical sensor? Temperature, pH level, interference from other chemicals, D is all of the above. So which one is the correct option? Yes, D is the correct answer. Why? More answers? Yeah, D. So answer is D, all of the above. So what a electrochemical sensor sense, it sends some chemical reaction and output will be in form of some electrical signal. Now you know that a chemical reaction to happen, uh, there will be like a certain temperature which is favorable for a chemical reaction to happen. Again, it may need some pH level so that the chemical reaction can happen. So these two parameters, temperature and pH level, that is very important for a chemical reaction to happen. So these two parameters definitely affects the chemical reaction, and hence a variation in temperature, a variation in pH level, that will also affect the performance of an electrochemical sensor. Next is interference from other chemicals. Now usually if you don't make your sensor very selective, like if you want the like conductivity of your sensors should change only due to specific say chemical, then only you will ignore the interference of other chemicals, but which is not usually true. If there is some like positive and negative ion, that will change the potential, that will change the current in your electrolyte or your in electrochemical sensor. So that is not very easy to ignore in case of electrochemical sensor. So interference for other chemicals also play a role in the performance of electrochemical sensor. So that is why the answer is all of the above. If there is any variation in these three, that will also change the performance or the output of the sensor. Let's go to week 5. So in week 5, the topics these were covered. First one was optical sensor. In case of optical sensor, we discussed first photodiode. So this is like a normal PN junction diode, we all know. So what happens in PN junction? So if the PN, so in case of photodiode, if you want to use it as an optical sensor, then the photodiode is operated in a reverse bias condition. So why we do that? Because in case of forward bias condition, the current in PN junction is already very high. Now if we operate in reverse bias, now say due to optical energy, so incident photon, which will create more electron and hole pair, that will actually change the overall current in your circuit. That may be high compared to the reverse bias current. Say in case of forward bias, that will be in hundreds of microampere. In case of reverse bias, that will be say in nanoampere current. So if due to some electron and hole pair generation due to optical light, incident light, then the reverse bias current will change, and that can be detectable. If the reverse change in reverse bias current is high, and if we have a measurement system that can detect say nanoampere and microampere current, so you will not use like a normal DMM for that. But if the current is sufficient enough and we have a measurement system, or we make a circuit to amplify that current, then also we can measure that current due to optical generation, and we can use it as a photodetector. Next is photoresistor. In this case, the resistance of the material changes due to optical absorption. So the change in resistance we can correlate with the optical signal, and we can say that we can use a photoresistor as a sensor. Now in optical sensor, there are a few concepts that were discussed. First is energy of a photon. So energy of a photon is E equal to h nu. Nu is the frequency, h is Planck's constant, and we can also write hc by lambda. So c is the speed of light, lambda is the wavelength of the photon. Now this photon, in case of metal, it will be able to remove an electron from a metal if energy is more than, say, some critical energy, and if this case is true, then it will remove an electron from the metal surface, and the total energy we can write as phi plus km. So this is the work function of the metal, and km is the kinetic energy of the ejected electron. Okay. Now in case of semiconductor, we know that if the band gap of semiconductor is easy, then the energy of the photons should be more than easy to create an electron hole pair, right? So in case of semiconductor, it should be more than energy of the band gap. So we can have a critical wavelength which is equal to actually like it is given by this formula 1.24 by Ez, which is in electron volt, and lambda we get in unit of microampere. So this is the critical wavelength for which we have electron hole pair generation. Now energy is inversely proportional to the wavelength, so the wavelength of any incident photon to create electron hole pair should be less than lambda c, then only energy will be more than the critical energy, so that electron hole pair can be generated inside a semiconductor. Okay. So these were the formulas, and then we had another formulas, let's say conductivity in case of a semiconductor is equal to nq mu n plus pq mu p, and essentially what happens when you incident light on a material in a semiconducting material, this NNP actually changes because electron hole pair is generated, so that changes the number of the concentration of electron and concentration of holes. That is how the conductivity gets changed, so the current or the resistance inside of a semiconducting material gets changed. So that is why we use many cases a semiconducting material to detect optical signal. Now as you can see that the detection also depends on energy. Say if a material has a very high band gap, Ez is very high, say, so in that case that Ez lies in, say, UV frequency range. So you want a material, you will need a material to detect UV signal which has very high band gap that falls in the corresponding wavelength falls in the UV frequency range, like UV wavelength range. So if the band gap is very high, then say you can use as a UV detector. If your band gap is such that Eg, so if it is equal to Hc by lambda, say lambda is in the frequency range 400 to 700 nanometer, say it is 500 nanometer in that case lambda, so you will be able to detect the light that corresponds to 500 wavelength, say I think it is maybe yellow or green, something that light. So based on your material you can design a sensor which can detect, say, specific type of signal. Next, the physics part related to magnetic sensors were discussed. So in this week we discussed two effects or two laws. First one is Biot-Savart law that talks about the magnetic field from a distance from a constant current source. So what were discussed, a magnetic field at a point at a distance from a constant current carrying loop or current carrying conductor, those were discussed. Again, I will not go into the details bit because we have already discussed these topics in week 5. Next was Hall effect. So Hall effect in semiconductor physics we mainly use to determine the the concentration of electron concentration and hole concentration in a semiconducting material. So that depends on so we apply a electric field and magnetic field, and we see how the carriers inside the semiconductor behaves depending based on electric and magnetic field. So based on that we can see whether the material is p type or n type, and this is the electron concentration and this is hole concentration. So here we discussed a term called hole coefficient, which is given by this formula RH, which is equal to 1 by n into q. N is the concentration of electron concentration inside a semiconducting material, and Q is charge. Now if we have the Hall constant value, then we can calculate what is our electron concentration inside the material. Okay. So these were we discussed. I am not going into details of it because it will take so much more time. So next we discussed about acoustic sensors. So acoustic sensors use sound energy. Okay. So acoustic sensors, because they use sound energy, they does not interfere with electromagnetic radiation. So these are very useful in certain situations. Say if it is a very hazy environment, there is a lot of dust, smoke, in that case also we can use acoustic sensor for measurement, because the sound energy or the sound signal is not affected by these. And typically we use ultrasonic sensor that has frequency above more than 20 kilohertz, because so we can hear from frequency 20 hertz to 20 kilohertz. So beyond that we cannot hear sound. So that those are ultrasonic sound, and if we use ultrasonic sound, then that will not border our day-to-day activities, but we can detect, we can use as a sensor, whatever the reflected signal, transmitted signal, that sound wave, based on that we can do detection. So these are acoustic sensor that we discussed in this week. Next were microfluidic sensor. So these talks about microchannels. Microchannels in micrometer dimensions. Now why we need microfluidic sensor? These are mainly used in case of biological sensor, where we want to mimic some the properties of some organs, say. Or microfluidic sensors are also used in case of biomedical sensors or biomedical sensing, where we have a very limited sample size. Suppose you want a sensor for which you need a blood sample. Now you don't want to take out a large amount of blood from your patient or some person, right? So if you make a microfluidic sensor, if your channel is in micrometer range, and even if your size of your sensor is very small, but it can efficiently detect the chemicals, those are in a blood sample, very accurately, then you will not need a large amount of sample. You can have a small blood sample, you can do the sensing, you can do the measurement. So that is why these are very useful in case of biomedical sensing or in case of biological sensing, where you have limited sample size but you want a very accurate measurement. Okay. So any doubt in this? So microfluidic sensors, again there are typically we use two types of substrate, either PDMS or glass, because these are flexible substrate and not flexible, these are transparent substrate. So if there is a channel and we want to flow a particular liquid through it, if the liquid has some color, say, we will be able to see from outside. So that is why we typically use a like a transparent kind of substrate in many microfluidic sensors, and glass is transparent and PDMS is like a flexible substrate, so it provides some flexibility and can be useful in many situations. To the questions. Ability to operate low visibility condition, high sensitivity, to sound frequency variation, non-contact measurement, D is high immunity, to electromagnetic interference. So what is the answer? So the question is, which one are the advantages of acoustic sensor? There can be more than one answer also. So let's see one by one. Uh, in case of acoustic sensor, the ability to operate in low visibility condition, this is one advantage, because in acoustic sensors can be used, say if it is if there is smoke or something else, because these are sound waves, this can travel through. If you want a if you want your signal to be an electromagnetic signal, which is like a visible light. Now you know, if it is a if you are using a visible light source for your detection, then if the visibility is low, say there is smoke, there is fog, then it will not pass through like we cannot see the target very clearly using visible light. But as these are sound wave, this can travel like towards your target even the visibility is low. So this is one advantage of acoustic sensor. Next is high sensitivity of sound frequency variation. So acoustic sensors are sounds like these are based on sound signal. So these are sensitive to frequency variation, but this is not an advantage, or I would say it will create some like noise due to frequency variations on frequency variation. It can create, right? So this is not an advantage. Next is non-contact measurement. So we can do non-contact measurement using acoustic sensor. Say you have a sound wave, it is traveling like this. Now say you want to detect this target, this wave will hit the target, it will come again back to your source, so it will be reflected back. Now based on the reflected signal and the time it takes for the reflected signal to come back towards the source, based on that we can say what is the distance between the source and the target. So we can do non-contact measurement without like physical contact between the source and the target. So this is one advantage in case of acoustic sensors. This can be used for some target detection under water also. So you know that sound wave travels like through water, so you can use a sound signal. If there is a target, if it is reflected by the target, then you can detect the signal underwater also. Okay, so this is one advantage. Next is high immunity to electromagnetic interference. As I mentioned, acoustic sensor uses sound signal, like sound wave. So these are not electromagnetic signals, so there will be low interference between electromagnetic signal and sound wave, okay, sound signal. So why we need like a low interference with electromagnetic signal? So we cannot see electromagnetic signal, but there are so many electromagnetic signal traveling like in the environment. We use our phone that uses certain frequency, certain electromagnetic signal. We use different electronic devices. There are antennas, there are different components that emits and that radiates and that collects different electromagnetic signal. That's how different communication channels are made. Now suppose you want, if you are making a sensor that is based on electromagnetic signal, that can interfere with other electromagnetic signal, those are already in the environment also. This problem will not be there in case of acoustic sensor because that uses a sound signal. Okay, so this is also one advantage. So the answer is A, C and D. So we don't have much time. Let's quickly go to week 6 and week 7. So in week 6 and week 7, in these 2 weeks we discussed about fabrication technique. So what are different microfabrication techniques? So this is deposition. This is the deposition of an uniform film. Okay. This is done, there are different deposition techniques, either PVD, physical vapor deposition, or chemical vapor deposition. Now in PVD we discussed about sputtering and evaporation. Then evaporation can be two types also: thermal evaporation, where you melt your material and that melted atom will like evaporate and it will be collected on your substrate. Okay, so this is thermal evaporation. And in case of e-beam evaporation, instead of like a heat energy, you will use electron beam to evaporate your material. So this is used in case of material which has very high melting points, say, where you cannot use thermal evaporation. In that case you use e-beam evaporation. And sputtering is also similar. You create a plasma of argon ions. Argon ions will hit your target, it will eject some material, and that material, those atoms will be collected at the substrate which is at the top. So this is sputtering. And CVD, so this is chemical vapor deposition. So certain chemical reactions are involved in this case. So there are different types of CVD: atmospheric pressure CVD, LP CVD, low pressure CVD, and plasma enhanced CVD. Those three we have discussed. Next, microfabrication technique was patterning. So in what patterning technique we had discussed photolithography, and in the next week we also discussed e-beam lithography. So what patterning means? It is the like to create a pattern, like create a pattern of a material on top of your substrate. So for that you will need like a selective removal of material, which is done by patterning plus etching technique. So that's how we can create a structure like this. Say this is your substrate, and suppose you are depositing your material something like this. So this is your, say, metal. So why you need that? Suppose you need two metal electrodes on for your sensor. Okay, so you can learn it by using patterning plus etching technique. Okay, I have discussed these topics in the live sessions also, so I'll not go into the details. Next is doping. So if you use a semiconducting material, then doping is done to increase or change the conductivity. You know that there, in case of silicon, there are p-type dopant like boron, so we can have p-type silicon. In case of for n-type silicon, we can dope it with phosphorus so that we get n-type material. And why we need that? Why we need p and n type doping? So that we can make basic devices like p-n junction. Okay, you know that p-n junction we can use as a photo diode and a photo detector. And from device perspective also, doping is very important, because in any device you will find like a p or n junction, or metal or semiconductor junction. So junction is very important. So from device perspective you can say that. And in case of from sensor perspective also, we can use those devices as a sensor. For example, we can use diode as a photodetector. We can use a MOSFET for detection of some chemical material, something like that. Okay? So that is why doping is important. Next is photolithography. So what are the basic steps in photolithography? First, we spin coat the photoresist on top of your substrate, or there can be a metal or other layer on top of your substrate. Then we do UV exposure. Okay, before that we typically do a baking after spin coat of the photoresist. Then we do UV exposure. We selectively expose some portion of the photoresist by UV. Now because of this UV exposure, say if it is a positive photoresist, the exposed part will become soft. Then we can do development. We can remove those soft part of the photoresist. Okay, so this is basic photolithography. After development we will get a pattern substrate or patterned photoresist, and on top of that we can do deposition and other etching or something else to get our final device. Okay. So this is one question on so this question is on optical microscopy and electron microscopy, but so I can discuss. So you have already done week 6 and week 7, so I think you can answer this question. So the question is, the wavelength of optical microscope and electron microscopes are. So what is the correct answer? Can you give me the answer in the chat box? See, the answer is that so in optical microscopy we use optical signal, that means visible light. Okay. So the wavelength in optical microscopy that will be in between 400 to 700 nanometer, right? So that is the visible light. Now what we typically in optical microscope, we use a yellow kind of light. Why? So I mentioned earlier that in clean room the light is usually yellow. Why? Because in clean room we do lithography, and in lithography we use photoresist, and photoresist are normally sensitive to UV light as well as blue light. So you don't want to change the properties when you are just looking at the microscope, right? So that is why a yellow or greenish kind of light is typically used in optical microscopy, because you will do you are just looking at the photoresist, you want to see the photoresist, and many cases the microscope can be inside in a clean room. That is why so that it does not change any property. Typically in case of microscope, like the light, you must have seen that the light is kind of yellow, which is close to 600 nanometer. If you look at the color range for different color for a visible light, then you will see that around 600 it is yellow and orange. Okay, so that is why in optical microscopy around 600 nanometer wavelength is used. Now in case of electron microscopy, why we use electron microscope? Now we cannot see like very small feature which is smaller than 600 nanometer using an optical microscope. Ideally we cannot see a feature which is less than 600 nanometer, but typically we see only a micron size in optical microscope. Okay. So the wavelength of electron is very small compared to this optical wavelength, and using electron wavelength we can see smaller feature sizes. So the wavelength for electron is given by this formula, h by p. So this formula is coming from de Broglie's wavelength. So the wavelength of electron is h by p, which is equal to h by m into v. H is Planck's constant, so this is 6.626 into 10 to the power minus 34 joule second. Mass is the mass of electron, that will be in the range. So in case of free mass of electron, that is 9.1 into 10 to the power minus 31 kg, right? And velocity, this will be in the range 10 to the power 7 meter per second in case of electrons, say. So you can do a quick calculation what will be the value of lambda. So you will see that it will be in a very small range. It will be in picometer range. Okay, so in these options you can see 0.012 nanometer, that seems to like a very small wavelength, and this can be the wavelength of an electron. Okay, so by looking at the options I can say that the correct answer is, for optical microscope it is 600 nanometer, and for electron microscope it is 0.012 nanometer. Okay, so the correct answer is A. So we are almost out of time. Let me quickly go through the content of week 7. So in week 7 we discussed again about photolithography and e-beam lithography. Next we discuss etching. So etching is the removal of material. So where etching can be wet etching, where you use a chemical to remove some part of your material, some part of your deposition. Then dry etching, where you use ions, physical by physically you remove some portion of your material, that is dry etching. Then in reactive ion etching, that is like a combination of both wet etching and dry etching. Here this is a dry technique because you will not use any chemical. Instead of that you will use vapors or like ions which are in vapor, like in a gaseous form. But because these are chemical species, there will be some chemical reaction at the material surface. So why we use reactive ion etching, even though it is expensive? So wet etching is generally very selective, so it will remove the material that you want to remove. But dry etching is it gives us very like anisotropic profile. It is very directional, right? So what is anisotropy and isotropy? We already know. So reactive ion etching gives advantages of both of these two. So that is why, if the process is very critical, if you are making a device which needs very good selectivity and very good directionality, then reactive ion etching is used. But this process is very expensive. The instrumentation cost is also very high. Next, we discuss different characterization techniques: optical microscopy, electron microscopy. I have already discussed this. Then AFM and STM, atomic force microscopy, we discussed. So this one is AFM. So using AFM, we actually get different like surface profile of our sample. Then STM is again this is STM. Using this also we can get the surface profile of our sample, but in this case the resolution is very high compared to AFM. So this is scanning tunneling microscopy, this is atomic force microscopy. All these techniques we use to see our material surface or material properties. Okay? So these are for material characterization. There are other techniques for device characterization also, but these were we discussed in week 7. Okay? So I think we are almost out of time. So let's stop the session here. For week 8, for the last week, I am taking another session like the usual session on Tuesday. I will discuss the concepts there, and we will solve some problems related to the topics. Okay. So is there any question? If there is no question, then let's stop the session here. Thank you everyone for joining the session. I hope the session was useful. Thank you. Important questions. So few questions I have already discussed in in the sessions, right? So you can revisit those. I have shared all the notes, all the PPTs, so you can see those, and similar questions will be there in exam. So you will get one notification, one announcement about the exam type and other details, but the questions will be similar to the assignments and the questions that we solved during the live sessions. Okay. Thank you everyone. See you on Tuesday.